In this video, I'm going to talk about averaging and subtracting data that has been collected using the liquid handling robot at the beamline. There are other tutorials looking at how we process HPLC data, SACS data, and how to get the scatter program onto your computer. So if you're interested, you can go and have a look at those. The idea here is that using the liquid handling robot, we will load one sample after another into a capillary in the X-ray beam and measure a series of images of that liquid. The liquid's not moving while we're collecting. We'll then wash and dry the capillary and load the next sample. Generally speaking, you would be loading a buffer first, you would shoot that, and then you would load one sample after the other. And basically what you want to do is average together all of the images from one shot, and then subtract the buffer and save out a single average subtracted DAT file for each. Okay, so in this window here I've done just that. This 6.0 is my buffer, so I've got 30 images for the buffer. There are some Nexus and H5 files in here. These are the raw data, so the H5 is a stack of images, the Nexus is a binary XML file that has all of the sort of beamline setup parameters in it. And then you can see 6.0 is the buffer, 6.1 is going to be the sample. This is a series of bovine serum albumin, BSA. 6.1 is at 5 mg per mil, and then I've collected at 2.5 mg per mil, 1.5 mg per mil, and so on down to a low concentration. Okay. So the important thing here is before we just blindly average the samples and subtract them, we want to know if all of the images collected of one sample are the same or if they vary. The reason they might vary, the main reason that they vary, is particularly with a protein sample, you'll get radiation damage as the series goes on. This is really why we collect multiple images and not just one image, so that we can have a look and see if there's radiation damage over time. 6.0 is a buffer. There's unlikely to be radiation damage in that. So I'm just going to quickly open this 6.1 series. This is BSA at 5 mg per mil. Oops. Okay, so I'm just going to drag these into the scatter channel here. This is in the Files tab. And there we go. You can see it's loading them up. Okay, and here we go. Just a quick point here, I had the auto RG checked, and so for each of these images it's going to try and calculate the radius of gyration. These are unsubtracted images, so it's not going to manage that, and so if you uncheck that, it'll load up a little bit quicker. Okay, anyway, here they are. Now, radiation damage usually appears in the low Q regime, and what you can see here is at the beginning of the run, you'll just have to trust me that these are the sort of early samples, we have a sort of a lower scattering vector down here, and then as the run goes on, it begins to move upwards in a sort of a fan. So this is very indicative of radiation damage, where basically the proteins are getting damaged by the X-rays. They are partially denatured and they begin to aggregate, and it's really the aggregation that we see rather than the radiation damage. Okay, so that's just a warning to say we do have to take this into account before we do the averaging. But let's move on to the subtract, the averaging and subtraction step. We're going to do that in a winner. So we go to the subtract tab. Okay, and we have two boxes here. This is the same as the HPLC. There's one box for samples and there's one box for background. Okay, so I am just going to load up my background files here. So I've selected them all and I'm dragging them into the background. I'm not going to bother checking if these are all the same. I actually know that they are for this run. I've obviously looked at this data before. You could check these if you wanted. One reason that they might not all be the same is sometimes when the sample is in the capillary from the robot, you'll find that the meniscus at either edge of the sample begins to drift a little bit, and if it clips into the beam, you might at some point during this run you'll get some sort of scatter spray off of the meniscus, and then as you get a portion of air into the beam, you'll see a sort of a drop in the signal at high Q. So sometimes you will have to be careful, and the step that I showed you before where you open them up in the Files tab, you can just have a visual inspection of what's going on. That can be really instructive, but I'm going to skip that in this case. Okay, so here is my sample data. Now, we've already seen that there's radiation damage in here. There's a couple of ways of doing this, just to show you a new feature of Scatter. One is I can just select all of these and drag those into the Samples tab. That's obviously a reasonably quick and easy thing to do. Another way, this is quite new, there's a Build List from File option here. So if I click that, I can then just select one of this set of images, and if I drag that in, it has automatically gone and found the other images in that set. Once they're loaded in, it unchecks the build list from file, so you're sort of back to normal working mode there. So that's really quite useful if you're dealing with large HPLC data sets and things. It's quite a useful feature. Okay, another useful feature here is if we hit signal plot now, I'll drag that into the view, you'll see that there is a sort of an upward trend to the I0. What this has done is it's subtracted the background and it's showing the I0, the total forward scatter. This is basically related to that. It's showing them for everything, and you can see there's a bit of an upward trend. Now, even more importantly, if I do add the radius of gyration to the signal plot and then I hit signal plot, okay, you'll see that the radius of gyration is also sloping up. You'll see that there are some outliers in here. This data was collected on the beam line while we were having an issue with beam stability, and so every 2 minutes you get a little spike in the data, and you can see that quite clearly in here. Okay, but let's not worry about that just now. Okay, so what you're basically looking for is how many images can I average together before the radiation damage becomes a significant factor. Now, in the I0, you'll see it's kind of flat here, and then it starts sloping up. And it's the same in the radius of gyration. You know, these to me look reasonably flat, and then we get this kind of upward slope here. So I would be selecting maybe, you know, that, okay? And just looking here, that's the first kind of 13 images. You know, I might miss this one out, so we'll go to 12 like that. Okay. So yeah, so that's that. That's us basically taking care of the radiation damage. The last thing we need to do is we set an output directory. I want to put this into. I'll just stick it into this folder here in my file system. I'm going to call this something sensible like BSA 5 milligrams per mil. It's good to avoid special characters in these kind of file names. Alphanumeric and underscore and dashes are fine, but try and avoid full stops and hashes and all, you know, all that sort of thing. Okay, and then we do subtract using selected buffer. Okay, and it's having a think. You can see it's processing there. And that's it done. Now it will automatically open up in your the active channel over here, and there's the data. Now there's just one thing I want to say about the data, and then I think I'll finish this tutorial. What its output is an average and a median. from those. And the difference between those two is the average just looks at all 12, 13 images that we just averaged together and subtracted. It's just the average of all of that. The median will sort of ignore outliers in that data set. And so if looking at this here, if you notice that the average and the median are significantly different, particularly down here where we were looking at some radiation damage effects, then you really need to go back to the data and just check again what's going on and why those two are different. But essentially that's how you would go on subtracting. So I would now, that was the 5 mgs per mil, I would now be going back, I could clear these, I could select my next data set, and so on and so forth. I'd do my signal plot again, I would select the images that are good, I would change my file name, 2.5, and then I would go on with that. Okay, so that's all. Thank you for listening.